Good morning, good afternoon, ladies and gentlemen. Welcome to the first of our three-session webinar series. I'm excited to be a host of this journey into data preparation for powder bed fusion printers with AM Studio. Today we have two expert presenters joining us. I invite Daniel Ploss and Peter Lettner. They bring a wealth of experience and knowledge to guide us through 3D printing intricacies. We encourage active participation, so feel free to ask your questions and engage with our presenters. Please input your Q&A in the Q&A tabs. Now, without further delay, I turn the floor over to our esteemed presenters. Over to you, Daniel.
Thank you, Gokul. So, one moment. Okay, hello everybody. A warm welcome to all our customers, prospects, colleagues, business partners all around the world. So we are broadcasting from Austria today. So just to clarify the kangaroo question, it's the tiny country in Europe, not to confuse with Australia. Okay, hello, let's start with the topic of data preparation for powder bed fusion with AM Studio. My name is Daniel Ploss. I'm responsible for the business development for our AM suite here now in Hexagon. So I'm at Hexagon since June last year. I'm part of Hexagon since the acquisition of CATS Additive. So I was the former sales director at CATS Additive. And before I did some experience in multi-jet fusion 3D printings on the plastic sides. And before that, I had my experience in CAD/CAM solutions. And this mainly on the sales side. And I'd like to introduce my colleague, Peter Leitner. He will give you the demo later and is our senior product engineer and responsible for all the technical questions around. Sorry, now I lost my screen. Sorry, responsible for all the technical questions around AM Studio and our AM suite. So we have currently 3 suites in production software. The first one is the classical production machining with the CAD/CAM solutions. We have mold and die with VC and Work&See. And the brand new one, our topic for today and the next webinars is the additive manufacturing suite with the product AM Studio as the heart from this solution, Esprit Edge to do all the post-processing, Simufact Additive to make high-end simulation beside AM Studio and also included in AM Studio with a small subset of these functionalities, and enabling products beside with Designer to do all the CAD functionalities and interface functionalities, and for sure the Nexus implementation for the whole workflow. This all functionality will be the topic for our next webinar next week. So then we dig deeper into these issues. But today it's the additive manufacturing suite. So for metal additive manufacturing solution for build preparation, process optimization, and also the workflow automation. So we have a high performance 3D printing software solution that is machine independent and CAD agnostic, empowering operational excellence in manufacturing prototype or production parts across industry ranging from medical to automotive and beyond. So we have really all our industries where we can deliver the solutions, and really from the first prototypes till big serial productions. The whole solution starts at quoting and planning and walks through the cycle till the delivery from our products. The topic of today is from preparation for manufacturing till the process simulation and optimization. In the next seminar, we also will dive deeper into the process simulations because it's a series of 3 seminars, also be available on our next webinars as well. And now looks to the AM Studio data preparation process, what we do exactly in AM Studio. So we're starting to import the geometries, either as a CAD file through the designer or directly STL file. Then we need to repair these files, find the right orientation, and on the orientation, it's start already to support with our heat maps beginners, and it's a very easy to use approach. Then it comes to supporting the part with the build plate to bring it stiff to the build plate because of all these tensions you will have in this procedure. So you need to connect the part with the build plate to prevent distortions, but for sure you will have distortions, and therefore we have the process simulation. With the process simulation, with the subset of SimUFACT, which is included in AM Studio, you can have a first guess to see which deformation you will have to make a pre-deformation, check if the support is stiff enough, and if everything is working, it comes to slicing and hatching. This is really the heart of additive manufacturing. We control the whole laser paths and powers for the jobs, and then we write the neutral format and translate it to our 3D printers, to our OEMs and partners. And for sure, we are working with the most big brands at the moment. So these are the companies which we included already very deep in AM Studio. And we have several ways to do that. So either we implement the API or do the whole slicing and hatching for that vendors. And for sure, we like to extend the amount and add new partners of OEMs to the system. So if you know new companies outside in the world, or you like to address with AM Studio, then just get in contact with us and we can implement them quite quickly. And for sure, what is the big USP of AM Studio? So it's a very easy to use solution with a guided workflow. So you can walk through the guided steps in AM Studio. Usually we have a half-day training for our customers. The functionalities which we implemented in the software are very high, and with a nice price, we reach a really good return on investment. So the product is for each company, for each customer, floating. We have really high-end slicing and hatching capabilities, and for sure integrated simulation with SimUFACT on a subset in AM Studio, which help also beginners to recognize what SimUFACT can do for them, and if they understood it, then they can extend to the full solution of SimUFACT. Here a small overview of some customers, mainly in the automotive industry, medical industry. We are looking for customers in aerospace. So as I said, so we have solutions for all industries. Here a small overview from the customers. And then we will dig in now into AM Studio itself. So Peter will start showing AM Studio right now, and then we have the Q&A session. If you have questions during the presentation, just write it to the chat, and then we can answer all these questions afterwards. And as I explained already, we have 2 follow-up webinars in the next 2 weeks. Feel free to join it. So that's from my side so far, and now I'd like to hand over to Peter.
Yeah, thanks Daniel for the informations that you gave to the audience. I want to start sharing my screen as well. Second. So I hope that you can see my screen now.
Yes, yes, Peter.
Yeah, thank you, Daniel, for the introduction. I also want to welcome you to the demo. I want to give you a short overview at first, and then we are more deep dive into the individual parts of AM Studio in the next roughly half an hour, so around about that. And as Daniel mentioned, it starts with the start screen where you can see the machine shop floor, which can be individually set up by the users themselves. And here at the top, there is this guided workflow that is also mentioned in the presentation from Daniel. So you have to first import parts and have to find a good orientation. Then you should support the part. So you need to position the supports underneath. You can make multiple copies of a part on the base plate. And then build process is subdivided in two steps. It's build simulation or process simulation and the slicing and hatching. And when you're finished with that, you can visualize the slices and hatches and can take a look at them. I simply want to take a SLM solutions machine for the first steps and load a simple part here. And as you can see here, it's the environment of AM Studio first time. On the left-hand side, there's a small structural tree, and on the right side, there's always a working panel, which changes depending on the actual step where you are in the workflow. You can jump back and forth in the workflow, so it's not a strict workflow in one direction, so you can always jump back. Yeah, that's the part that I want to first show. And as Daniel mentioned, first thing is that we have to find a good orientation for the part, which is a major step in the whole data preparation. Therefore, we developed the so-called orientation maps. I also want to go into details here later on. I can find here a pretty good orientation, for example, this one, which is a very high and a very low shadow on the base plate orientation. And I want to work with this orientation for the first steps. And when the orientation is found, I can jump over to the calculation of the supports. You can find all the regions for this pretty easy part, or for this simple part. We only have to support the bottom area here, which are these two small surfaces here on the bottom. And then we are more or less done for the supporting for this part. And next step will be to make multiple copies of a part. I want to show you here a new functionality, which is available in the 2024.1 version of AM Studio, where you can now make a sort of an assembly of parts, and you can then nest those assemblies. So you can, we want to position these parts a bit interlocked, let's call it in this way, and we can now simply select both parts, position them, for example, here, and we can now set them up in a way that I want to have in X direction 10 parts and in Y direction 5 parts, and some distances which have to be defined here. And then the manual nesting algorithm can now use this assembly and make multiple copies of this assembly here on the base plate. So probably this is the setup I wanna work with, and I'm finished with the nesting. Next step, which is subdivided in process simulation and slicing and hatching. Process simulation is then, as Daniel mentioned, the Simufact additive implementation of functionalities inside AM Studio. So we can now run a process simulation. So we can take a look how the part will be formed during the print process, and find out critical areas. This is one thing that is very beneficial within the simulation, and the other thing is that we can also use the simulation results to pre-deform the part. So now the simulation is done. Also new in the 2024.1 version, we have changed the visualization from a simple voxel result representation to a surface representation of the results. So now the results are mapped onto the real surface of the part, and it gives more details about the deformation of the part. And what you can see, there are two steps: part finished, which means part is still remaining on the base plate as printed, and then part plate removed means that the part is cut off from the base plate. And what you can pretty good visualized here is that due to the fact that they are not stitched to the base plate anymore, these two, let's call it feet, will bend a bit to the outer direction. It's not much, it's about 1.2 millimeters, around about that. If this is too much, then you can work with a pre-deformation. What means pre-deformation? I can take the results from the simulation, which are the blue ones in this infographic, and I can pre-deform the part in a way so that when we print this part, the model will be, or the output will be an accurate one. For this part, I don't want to use this one, or I don't want to use a pre-deformation because the deformation is not that big. Next step, as I mentioned, we have to define the slicing and hatching profiles. We can access to all the parameters here. So for example, for the slicing, we can, or for the hatching, we can access to every parameter in the slicer and hatcher, so the hatch distance, the stripe offset, so how the machine will later on process the part on, or the layer on the machine can be defined here. For some machine vendors, you can have the full access to all the parameters. For others, like for example, for the EOS machines or for the Trump machines, we are using the slicer and hatching approaches from the machine manufacturer, so that it's guaranteed that the qualified process parameters are used. By simply hitting on generate build file, I can now start the slicing and hatching, and when it's finished, can take a look at each and every layer and each and every vector, so that you can see here all the layers on the left hand side. And when we zoom in a bit, we can also find all the single laser paths, how they will be proceeded, and so on and so on. So yeah, that's more or less the file which has been generated now. The SLM file is stored in a defined location, and I can execute it on the machine. So far, to a quick overview of how AM Studio is doing the data preparation. I now want to restart AM Studio and get more into the details of some functionalities. Especially, I want to begin with the orientation maps, and therefore I want to load a simple part. As you can see here, as soon as I import a part, you can see that we are analyzing the part if the geometry is a valid one, which means are there any open edges or intersectional triangles inside this part? Because otherwise, when we are working with non-manifold meshes, we can run into problems later on when we are slicing and hatching the part. So that's the reason why we are focusing here on working with valid parts. By simply using this healing functionality, the algorithm is trying to get aware of all these errors In this case, we get a summary here on the right hand side, errors before healing and errors after healing. So now the healthy pack is a green one, so it's good, the part we can work on. As I mentioned before, orientation maps, it's a very important step to find a good or bad, to find a good orientation of a part, and therefore I want to deep dive a bit into the orientation maps. And what you can see here, there's this two-dimensional map, and you can find inside this orientation map every orientation of the part inside the build chamber. And you see here 3 different criteria where you can take a look on. First thing, which is very intuitive, is build time or speed. The speed or the print time is low when the part is orientated pretty flat. In comparison to that, a high orientation of the part is bad in context of build time. The reason for that is pretty simple. The volume that has to be exposed is always the same, but you have to do more recoder movements, and so the build time will increase. So good orientation, a green one or this green one, which are more or less from the build time equivalent, and as well the bad ones can also be seen here. And it's what I think is pretty beneficial is that you can see that there are more good and more bad orientations due to the fact that this part is symmetric. You have to find 2 similar orientations here. Another criterion is the support volume in this case. And for example, I want to go into a red orientation, which indicates bad orientation in context of support volume. And what you can see here, there are a lot of surfaces highlighted in rainbow colors from green to red. And these surfaces indicate support surfaces. So these surfaces have to be supported later on. And as you can see, there are a bunch of those surfaces which have to be supported, and as well they have a certain height from the base plate. In comparison to that, you can see in a green orientation, we only have to support this bigger area here on the bottom and some smaller features in the inner. But yeah, I think it's pretty intuitive that this is a better orientation than the ones before. And last but not least, we are calculating a tendency of distortion. And again, a red orientation indicates a bad orientation in context of deformation. The reason for that is pretty simple to describe. So we are searching here for an orientation which is where the build-up is homogeneous and the XY expansion of the part or of the slices should be small, due to the fact that when you have a big expansion in the X and Y direction, you have to deal with more stresses due to the shrinkage of the part. And this can be pretty good seen here. The red orientation indicates a big XY expansion of the part. In comparison to that, there is this green orientation where you can see it's also a very homogeneous buildup, but a much smaller XY expansion of the part. Another criteria can be the shadow, which is highlighted here in the or which can be found here as well. It's also a new feature in the 2024.1 version that the shadow is visualized in AM Studio. And as you can see here, there are again 2 green orientations and 2 red orientations. And as you can see there on the bottom, the shadow is much bigger for the red orientation than in the green one. And now I have to find a weighting for those 3 individual criteria, and therefore we can use this triangle. And as you can see, you can weight the different criteria by simply moving the cursor here in the inner of the triangle, and you get a new current setting map. And then you can simply find an orientation which is, depending on your weights, a good choice. I want to leave it for that part with this orientation and load some additional parts here for the later describing of the different support types which are available. And I want to move them a bit. And this part can also be orientated with the orientation maps pretty good. Again, we are taking a look at the shadow and jump into green orientation here, for example, something like that. And then we are good to go with this part as well. As mentioned before, next step after the orientation is done, we have to support the parts. And I want to start with the tooth implant part here. And we are offering different support types for the users, depending on the needs or depending on the part themselves or on the regions. You can decide which one is a good orientation or which one is the beneficial support type for this part. I want to start with the rod supports. What are rods? You have simple points on your region, and they are represented as tubes in this case because they are pretty easy to scan later on the machine. And on the top there is a cone-like structure which you can set up on your own way. The reason for the cone is pretty easy to understand. You can, with the cone structure, you can easier remove the supports from the part, and by setting up them in a beneficial way, it's more easier to remove them. What I want to show you here more in detail is the different sampler strategies that we are using, and it's a sampler pipeline. So we are starting with finding local minima inside a certain support region. So for example, here you can see there's a lowest point here, and this lowest point has to be supported because otherwise the scanner will, or the printer will begin in loosen powder with the geometry, and this is not a beneficial approach. In addition to these mean points, we can sample the region with regular grid sampler, which more or less indicates, as the name mentions, you're regular sampling the region, so that you are finding the points for the rod supports. But in some cases, this is not really beneficial because there are some areas where the points are missing, and therefore this last sampler strategy, the Poisson sampling, which is a distributional function, is then applied onto the region, and then you end up in a very beneficial way of supporting the part. These supports are mainly used for smaller areas. So in this case, it's a tooth implant. They are pretty small support regions, not really high from the base plate, and they are very easy to remove. So this is very beneficial for removing those parts. The reason why I pointed out the sampler pipeline is we are using the same strategy for finding these initial points for the tree support as well, and we offer here two different default strategies: the to mesh tree support, and as you can see here, the algorithm is trying to attach the mesh as soon as possible, and in comparison to that, we have a two platform tree structure, which is more or less trying to get aware of attaching the part in a certain, in any way. And as I mentioned beforehand, the initial points here are found by the same sampler pipeline as I defined it before, as I described it beforehand. Another support type which is also very often necessary is line supports, and I want to use this one here. What are line supports? You can find lowest lines in parts due to the fact that they that there is no surface, or that the surface doesn't fulfill the overhang angle to be a support region, but there is a lowest point here. You have to set a certain support underneath, because otherwise, again, you're beginning in loosen powder. And therefore, you can use this line support structure, or what we also, but what's also oftentimes used for the line supports is you can use a block support structure, which is called line thickening. And as you can see here, this lowest line is now thickened, and it's more or less a volumetrical or a surface then get generated out of that, and this surface can then be supported with a certain support type, the block support in this case, which I want to describe here more into detail on that part. There's a bigger area here, and the block support is more or less the most used support type in metal AM. So it's a very regular structure here. So you can define the spacing. So what is mentioned by the spacing is the distance between these single walls can be defined here pretty easy. And there's a surrounding surface which is called contour. And in comparison to other software vendors, we are using here a smoothing algorithm, which is pretty beneficial to get aware of a lot of scanner movement in the contour, which is pretty beneficial for the scanner itself. And on that part, I want to show you also the possibility of editing the support region. For example, you can simply edit a region by removing some triangles here. For example, I do not want to support the area here in the inner. So probably something like that. Apply, and again generate, and then this surface is no longer, these triangles are no longer supported anymore. And one other thing is pretty beneficial. You cannot assign one single support type to a region. You can mix supports onto one region. So I have added here a block support, or I have generated a block support, and I can add an additional support. For example, here on the contour, I can add so-called contour sampled tubes. This is the sample that I did not describe beforehand. The contour sampler more or less positions additional points on the contour of the part of the region and adds more stiffness to the region. Exactly. And last but not least, there is this bigger topological optimized part, and for this one, I want to show you the functionality of the region list. You can list all the support surfaces in this region list, and you can filter based upon different criteria or properties. So the triangle area, or the part-to-part fraction, which more or less means the amount which is from, if the part-to-part fraction is 0, then it's the support is only generated from part to the platform. When it's 100% part to part, then the surface is only in the inner of the structure. And with this width, for example, I can find big regions which have a certain expansion and which are more critical, and there I want to show the last support type, which is the cell support type, which is very beneficial in the context of saving support material, because what you can see here, we are generating small support structures near to the support region. And when we are getting away from this support region, the cells are getting bigger and bigger. So you can save a lot of support volume. And the other thing is that the powder which is stocked in the inner of this support structure can be easier removed due to the fact that there are bigger holes where the powder can be easier removed, or can be easier came out of the structure. For all the other support on this part, I want to use a tree support structure, and then I'm done with that part as well. Exactly. Yeah, so far as a quick overview of all the support types that we are offering. As I mentioned before, it very highly depends on the part itself, which support type is beneficial. I want to skip nesting because I showed it in the introduction more into details. And what I want to show you again is the functionality of the simulation, because again, I want to increase the voxel size, which is more or less dealing with the accuracy and the calculation runtime or the calculation time for the simulation. And it's a fully embedded simulational capacity in AM Studio, so you do not have to export the parts loaded in Simufact, import them into Simufact Additive, run the simulation, do the pre-deformation, and then import the results. So it's fully embedded in AM Studio. You can now run the simulations with up to 4 cores. And a new capacity in the 2024.1 is the base plate removal functionality. So you can simulate until part is finished and remaining on the base plate. As I mentioned before, you can see it here pretty well, that there is no deformation on the bottom here of the part, because it's fixed onto the base plate. And last step is when you remove the part from the base plate, you can see that it will bend a bit the whole structure due to the fact that it's no longer stitched to the base plate. So the inherent stresses and the strains can be relieved, and so yeah, and so the deformations can be done in a different way. The deformations here in this case are 0.3 millimeter, but more or less not in the structure, in the supports. In the next release, we will also offer the functionality of support removal, so you can also then simulate how the part will deform when the supports are also removed, and then you can see the results. We can apply now a deformation or pre-deformation in this case. So we take the simulational results, pre-deform the part in a way so that it's beneficial then later on. And again, last step, we can now assign certain scanner profiles or slice and hatch profiles. I have a list of different profiles here, and I simply select the parts and can assign, in this case, a aluminum parameter set to the parts. Clicking on generate, running the slicing and hatching with our very fast approach that we have developed here to calculate all the laser passes. And you can now again visualize all the slices, all the hatches, and you can slide through all of the different vector types. And last but not least, what's interesting for the user or for the customer, we can calculate a cost estimation based upon the vector result. So we now know each and every vector. We can calculate build time. In the settings area, you can define machine hour costs. We have calculated the material amount which is necessary for the parts, and so we will end up in a in print cost for this certain print job, which is not a full build plate. It's a pretty small setup of 416.1 euro, and subdivided into machine costs, material costs, and a certain profit. Exactly. So that's more or less it that I wanted to show today.
Thank you very much, Peter. Thanks for this awesome presentation for EM Studio. We have 3 questions left from the audience. So the first one is, what are the compatible metal printers for EM Studio? So these are the printers I showed in the beginning of the presentation. You will get the handout after the webinar, so you can read it. But the big brands like DMG, Trump, EOS, SLM Solutions, Forsoon, 3D Microprint, and ePlus3D. But you can read it later very easily, and it's quite easy to add new vendors to the system. Just give us a call, and then we can discuss how we should proceed. The other question is why supports are added to the part when we are using powder material which acts as support. So I think this question is related to powder bed in plastics 3D printing. In metals, you have a lot of tensions, and these tensions need additional support. If you work with polymers in SLS or powder bed fusion, then you do not need the supports. But in powder bed fusion for metal printing, it's absolutely necessary. And a third question I like hand over to Peter. What are the possible results or graphs the user can take from the simulation tool in the EM Studio?
In the actual implementation, the results which are visualized in EM Studio are only the deformations. We are working, or we will in a later release, we will also offer the stresses, the strains as results. But the most important one from our point of view was the distortion, because this is what's really critical. So when the distortion is massive or is big, then you have to act. You can add more supports, or you can use the pre-deformation to get aware of these deformations. But yeah, in the future we will also offer other result types like stresses, like strains. In the actual implementation, we only have the deformation as a possible result visualization available.
Okay, then another question dropped in. We face a deformation in SLS for flat large parts. Did the software to repair this deformation? So in our case, we have it just in powder bed fusion for metals, but I think the SLS functionality is part of the SimUFACT simulation, and this we will show in this seminar, maybe when we have the issue of simulation as well next week. But we also can maybe link you with the SimUFACT team, and they can offer you a solution for SLS as well. So no more questions at the moment. If no more questions are coming in, then I like to say thank you to everybody. Feel free to get in touch with us. We are happy to discuss also face-to-face or discuss customer projects from you, or directly some benchmark files. Yeah, so it's on you how you like to proceed. We are here. Some words, end words from you, Peter.
No, thank you for the into the whole audience. Yeah.
So see you next week or in face-to-face communications. Bye-bye.
Bye.
For dialing in.